Okay, so with our first one here, we have Tyrone soldering two wires together. He has to raise the temperature of the wires by 70 degrees. So they just gave me delta T, 70 degrees Celsius. The wires have a mass of 0.34 kilograms. 0.034 kilograms. Okay, and are made of copper. So C is 0.39 joules per gram degree Celsius. Okay, we're looking for how much energy he has to apply to the wires. So E equals MC delta T. Do I have all three of those things? All right, so this one I don't even have to manipulate, right? I just have to plug the numbers in. So we got 0.034 kilograms times 0.39 joules per gram degree Celsius times 70 degrees Celsius, right? That should give us 928.2 joules. Okay. Questions on the first one?
Since it's in kilograms, do you have
Oh, sorry, was it in kilograms?
It still works.
Oh,
But
but I should have converted it to grams, which is 34. I didn't see
to
that.
change it, do you just times it by
Times it by 1,000, yeah. 3.4, sorry, 34 grams, 34 grams. Where's my eraser? That's why it comes out to a much bigger number, because all those decimals don't come out to 928. Okay. Actually, it should be, sorry, I put 3.4, it's 34. 34, now it looks better. Okay. All right, how many people have done 11? All right, I'm going to give you 2 more minutes on 11 and see how we do with that one. So we've done 1 for E and 1 for T. If you're done 11, try 16, because we haven't done one where we calculated mass yet. Okay, let's look at 11. So we got Brianna boiling water to make Kraft dinner. Okay, she applies 60,000 joules of energy. So they told us what E is. Okay, 60,000 joules. And it's 1.4 kilograms, which is 1.4 liters of water, but that is in grams, 1,400 grams. Okay, and we're looking for how much the temperature increases by, and of course, because it's water, the C is 4.2 joules per gram degree Celsius. All right, E equals M times C times delta T. I'm trying to solve for delta T, so I'm going to divide both sides by M times C. Okay, and so what I'll be left with is 60,000 divided by 1,400 times 4.2. Okay, and when we do that, we should end up with 10.2 degrees Celsius. Okay, questions on 11? All right, how many people have done 16? Okay, I'll give you a couple more minutes and then we'll look at 16, and then we're going to move on, because these don't require a ton of practice. Okay, so let's have a look at 16. Okay, so we have Kara who's making Ichiban. Okay, that's the ramen noodles. I used to live on that stuff, especially the chicken flavor, so good. Okay, all right, so she's got to heat water. So right away they tell us the material. So we know that C is 4.2 joules per gram degree Celsius. Okay, she's heating the water from 50 to 100 degrees Celsius. So my temperature change is 50 degrees Celsius. Okay, and she uses 1 million joules worth of energy. Okay, what mass of water is she heating? All right, so I've got E, I've got C, I've got delta T, and I'm looking for M. All right, so if E equals M times C times delta T, and I want to isolate M, I just divide both sides by C times delta T. All right, and I'll be left with 1 million joules divided by 4.2 times 50. Okay, when we do that, we get 4,761 grams worth of water. That is 4.7 liters of water. Someone who's made a lot of Ichiban, that would be enough for 8 packages. Actually, almost 9 packages, actually more than 9, okay? Because each one only takes 500 mils of water to make, okay? So yeah, that's a lot. Even I wouldn't eat that much in one sitting, at least. All right, any questions on how those work? All right, pretty straightforward formula to use. 5-mark question on your unit exam. Easy peasy.
That number divided by 500 is 9.5, so that's 9.5 bags of
9.5 bags, yeah. 4, because 4,500 would be 9, right? Okay. All right, we're gonna move on to the next thing here. So that will be, oh, sorry, the latent heat stuff. All right, so I just need to find this next thing, need you to find this next thing in your notes, okay? We've been talking about latent heat, okay? It's a way that energy gets transferred from more equatorial parts of the world to more northerly parts of the world. It's that energy that's stored in water vapor. And as that water vapor moves from one place to another, it takes the energy that was required to evaporate it. And when it condenses and falls as precipitation in the new area, it releases that latent heat, effectively transporting large amounts of thermal energy from one place to another, right? Now we're going to look at where does that energy come from and how much energy are we talking about, okay? Because when we've been talking about it, it's like it's there, it's an amount of energy, but we haven't really been specific, okay? You're going to see now just how much energy is stored in water vapor, okay? And it's a lot, right? But that's not the only kind of latent heat there is. Okay? There's also latent heat in liquid water because it's one state above solid. Right? Anytime you change the state of something, okay, from solid to liquid or liquid to gas, right, there is a change in the potential thermal energy of that material. Okay? I say potential because you can't measure it with a thermometer. Okay? In case you haven't noticed this, when you put ice in a drink, the ice or the temperature of the drink doesn't change until all the ice is gone. Then it'll start to go up again. But as long as there's a little bit of ice in the drink, the temperature will stay around freezing. Okay? Once the ice is gone, then the rest of it will go. Because it takes a lot of energy to melt the ice. You've had this experience. You've all made a snowball with your bare hands at some point. Okay? Do your hands get really cold really fast when you're doing that? Like way faster than if you just hold your hands up in cold air, right? Right? Why do they get so much colder when you're making a snowball with your bare hands than if they're just out in the cold? Well, not so much that your hands are warm. Your hands are warm either way, even if I just hold them out in the cold air. My hands are still warm. But what are my hands doing when I'm making a snowball? What happens to the snow? It does get compressed, but it also, when it comes in contact with my nice warm hands, it melts. Yeah, and it takes a lot of energy to convert ice into liquid water, right? And where does it get the energy to do that from? From your hands, okay? And according to what we know of work energy theorem, conservation of energy, if the ice is gaining it, my hands are losing it, okay? So my hands get colder, right, in order to melt the ice. Now, the ice, while it's melting, doesn't get any hotter. It's at 0, okay? Ice and liquid water both exist at 0 degrees Celsius, okay? My hands are obviously much warmer than that, and that's why their temperature goes down. They're not changing state. Okay, but the ice is, right? So, latent heat can be changed at 2 different points in what we call the heating curve of any material. We're only going to deal with water in this course. So this is the heating curve of water. If water is below 0, it's in what state? It's frozen. It's a solid. It's ice. Okay? If we heat it to 0, it will melt. But there will be a short period of time while it's melting that I'm still adding energy where the temperature won't change. Then once all the ice is melted, the water will start to do what? It'll start to get warmer. Okay? That would be this part of the graph here. Okay? So this is the part where I'm warming up the water. I'm changing its temperature. Right? Once it gets to 100, it stops changing temperature again. Okay, you can try this at home if you have a thermometer at home. Okay, put it in a pot of boiling water. It doesn't matter how long it sits in there while the water's boiling, it will stay at or near 100. Okay, and it'll stay there until all the water is gone. You don't want that to happen, by the way. You don't want to boil off all the water in the pot, okay? Because it leaves behind all the salts in the pot, and then they burn onto the pot. Really hard to clean off, so don't take the experiment that far. Okay? Just boil the water, and you'll see that as long as it's boiling, it doesn't get hotter. Okay? You can't make water get hotter than 100 degrees Celsius under normal conditions. Okay? Is there a way you can make water hotter than 100 degrees and keep it a liquid? Anybody have a pressure cooker? Okay, like those, what do they call them? Like a Ninja? No, not a Ninja. What do they call them? Anyway, it's a pressure cooker. You crank it on and it'll increase the pressure inside, which means the water will stay liquid up to like 150 degrees. Will that cook things faster? Yeah, you always cook things faster at a higher temperature. Okay? We can only, in normal conditions, get water to 100. Okay? Because after that, it'll boil off. Okay, and it won't get any hotter than 100. Right, everyone kind of following me there? All right, if we look at this graph, okay, because this graph is built correctly, on the x-axis is heat energy. So how much thermal energy I'm adding. Okay, on the y-axis is temperature. Okay, so if we're looking at this, obviously some parts of this heating curve take more energy than others do. Okay, so does it take very much energy to heat ice up? Right, like I go from -25 to 0 and I barely add any energy. Okay, now anywhere where the graph is going up, the temperature is changing. Okay, so anywhere where the line goes up, there's a change in temperature. Okay, and because it's ice, do I know the specific heat capacity of ice? I do, because it's on my sheet here. It's 2.116 joules per gram degree Celsius. During this time here, and this time here, and over here, the temperature changes. Anytime temperature changes, you are changing the kinetic thermal energy. Okay, because temperature measures the kinetic thermal energy of a material. It measures basically how fast the particles are moving. Okay? That's how a thermometer works, incidentally. Okay? The more often, or the faster the particles are moving, the more often they hit the thermometer. Every time they hit the thermometer, they transfer kinetic thermal energy to it. Okay? And so the alcohol or mercury or whatever's inside expands and goes higher up inside the tube. Right? So it measures the kinetic thermal energy, but it doesn't measure the potential thermal energy. The potential thermal energy of a material is based on how close together are the particles. Okay? In a solid, typically, the particles are pretty close together. Water's an exception simply because water's polar and it does that weird thing and expands. Okay? But the molecules can't pass each other. It's crystalline, so they can't move past each other. Okay? In a liquid form, they can, right? It flows, the molecules can move around. And as a gas, they're even further apart. Okay? So they have more potential thermal energy. Okay? And so in order to get particles to move further apart, I've got to add a lot of energy. Okay? If they're in a liquid state like this and I want to turn them into a gas, I've got to add even more energy to separate them further. All right? So there's two kinds of thermal energy. Kinetic, how fast the particles are moving, and potential, how close together are the particles. Solids have the least amount of both. Okay? Liquids have a little bit more, and gases have the most. Okay? All right, so if I know that this ice is going to go from -25 to 0, and let's say I have, I don't know, 100 grams of it, okay, could I calculate how much energy would be required to do that? If I knew its mass, I knew its specific heat capacity, and I knew its change in temperature. Right? Those are all part of E equals mc delta T, right? The formula we learned yesterday. Okay, so anywhere where the kinetic thermal energy is changing, we can calculate that change in kinetic thermal energy using the formula we learned yesterday. This deals with kinetic thermal energy. So anywhere where the line goes up, we would use E equals mc delta T to calculate how much energy would be required at that step. Now, that formula won't work here or here. Why not? It's not changing temperature. Yeah, I have to put in a 0. And clearly, according to this graph that says energy is increasing during those parts. 0 is definitely not the correct answer, except it is. I'm not changing the kinetic thermal energy of the material here or here. These are the two spots where I'm changing its latent heat, its potential thermal energy. There's different formulas for calculating that, okay? And they're really easy. And you won't even have to manipulate them, ever, okay? You'll just have to plug numbers in, so they're really, really easy, okay? All right, so we got to look at a little bit of practical application. Obviously, it doesn't take much energy to raise the temperature of ice. Okay? It has a low heat capacity, okay? And so it changes temperature quickly. But it does take a lot of energy to melt ice. We know that when we make a snowball, our hands get really, really cold. Okay? Melting ice, if you put a block of ice in a pot, it takes quite a while to melt it all. We put ice in drinks, and they can last for quite a while. Okay? They can stay cold because it takes a lot of energy for them to melt. That's the whole reason why we do that. Okay? Putting ice in a drink keeps it cold because it's absorbing energy from the drink in order to change state. Okay? Now, eventually, that's going to dilute your drink a little bit, right? But in the end, it keeps the drink cold for a long period of time because it's a heat sink. Okay? These things are going to change state eventually from solid to liquid, okay? And that entire time, they can absorb heat energy from the drink. Okay? Now, once I get all the ice melted, if I keep adding heat, it's going to get hotter. Okay? And I can calculate how much energy that would take, again, with E equals mc delta T. The only thing that would change is now I'm dealing with liquid water, which has a different heat capacity. Again, water's weird. Okay? Most things do not have a different heat capacity for their solid, liquid, and gaseous form, but water does, because water's polar and it's the exception to every rule. Okay? So it actually does have different heat capacities. So I can calculate that. Once I get it to boiling, it's going to boil for a really long time, okay? Because it takes a ton of energy to change water from a liquid to a gas. Okay? Have you ever heard this kind of warning? Be careful about steam. Steam will burn you worse than water. Okay? Most people just think it's because steam can be hotter than water, and that's certainly part of it. But the other part of the reason why water or steam can burn you worse than water is this. This part right here. Water at 100 degrees would only have this much energy. Steam at the same temperature, steam at 100 degrees has this much energy, even though they're the same temperature. Okay? But steam has had its particles moved away from each other. It has more latent heat energy than the liquid does. So if steam hits my hand, it will condense back into a liquid. And when it does that, what happens to all the energy it had? It gets released. Where does it go? Onto me. That's a deep tissue burn, okay? Because that's a lot of energy. In fact, it's more energy than the water has, period. Okay? And that's just because it's steam. It also has all that other energy. Okay? So steam carries a lot of energy. This is why we're saying latent heat is a big energy transfer mechanism. Okay? Because every little tiny droplet of water vapor that's moving from one place to another carries with it a large amount of energy. Okay, let's look at a couple other applications of this. How do our bodies keep themselves cool when it gets hot?
We sweat
Okay, why does that work?
because you're releasing energy.
Okay, well, you're releasing water for sure. Okay, but it's actually not so much that there's energy in the water. What happens to your sweat? Hopefully,
It evaporates?
it evaporates. Okay, so when I sweat, I've effectively got water on my skin that's right here. Okay? When it evaporates, it loses, or it takes energy from my body in order to evaporate. This much, right here. Okay? So can I lose energy rapidly if I'm evaporating my sweat? Yeah, very rapidly. The only place that your sweat gets energy from in order to evaporate is you. Okay? So you can lose large amounts of heat energy by evaporating your sweat. Okay? Very large amounts. It's why it's really dangerous if you get sweaty in cold weather and then you suddenly stop your activity, because you're still wet. Okay? And all that sweat's got to evaporate, and it's going to take your energy to do it. And it's why they tell you dress in layers, right? You take layers off so you don't get overheated, or if one layer gets wet, you can take it off and put other layers back on that are dry. The worst thing you can be in the winter is wet, okay? Because that water's got to evaporate. It's why it's such a big deal if people fall through the ice, okay, in the wintertime. They crawl back out, they're soaking wet. It doesn't have to be that cold for that to be a dangerous situation. They're wet, and that water has to evaporate, okay? So, you maybe noticed this, sometimes like at Stampede, if you've gone to Stampede on the really hot days, they have those misting cooling stations, okay? You walk through those, it's not that the water is all that cold, it's just mist. And in fact, it's gone through a hose that's run across the asphalt. It's probably really hot, actually, okay? But when it hits you, okay, it starts to take energy from your body in order to evaporate. So you feel a little bit cooler. It's also by sitting in front of a fan makes you feel cooler. Is the fan blowing cold air on you? It's just blowing the air in the room around. It's the same temperature as the air when you have it on or off. Okay? But what happens is because the air is moving past you, it helps the water or the sweat or perspiration, whatever, to evaporate more quickly. Okay? So you feel a little bit cooler as a result. Okay? In fact, if you get hot, you're better off to move around than to sit still. Because if you move around, your sweat will evaporate faster. And it's counterintuitive. We're like, oh God, so I'm just going to lay here. No, you should actually move around if you want to cool off. Okay? It's actually better for you. Making some sense? Okay, so is it good to sweat a lot or a little? Which would be better? I mean, because we all know those people, right? There's some people and they only just perspire a little bit. They get that little sheen of perspiration and that's it. And then there's other people who drip. Okay? Which is better? Well, in terms of conserving water, perspiring lightly is better, okay? But perspiring or sweating heavily actually doesn't cool your body any better or any worse than just perspiring does. Okay? It has to evaporate. If it's dripping off of your body, it's not doing that job. Okay? Once it drips off your body, it can't cool you anymore. Okay? And some people, they really sweat. Okay? I played basketball with a guy in high school. He would have to, he wouldn't wear his uniform shirt during warm-up because it would be soaked by the time warm-up was over, because the guy, if you set a screen on him, you'd slide off because he would just be slimy, okay, all the time. Okay? The Oilers used to have a goalie named Nikolai Habibulin. This guy would lose 10 pounds in a game just in sweat. Okay? He actually drilled holes in his skates to drain the sweat out of his skates, or his skates would fill with sweat. They actually caught it on the crease cam one time, the little camera they got at the bottom of the goal. Okay? You could see the sweat dripping out of his skates. Okay? That's why the Oilers were so bad in a shootout back then, because the guy was all cramped up and dehydrated by the time the shootout came. It was useless. Not that it was all that good before that, but okay, he would just sweat like crazy. Every time there's a stoppage in play, he'd go over to the bench and get a new blocker and a new mitt. Okay, and the guys on the bench would go like this. Yeah. And literally wring the water out. The guy, it was disgusting how much the guy sweat. Okay? Didn't mean he cooled himself any better. Okay? He just sweated a lot. Okay? And some people do. Okay? But it doesn't mean that you do this any better if you sweat a lot. Okay? All right, so here's what we're going to look at. We're going to look at the kinds of problems we might run into for these kinds of situations. Now, we talked about how we use E equals mc delta T to calculate the changes in kinetic thermal energy, right? So anywhere where the line goes up, we use E equals mc delta T. But as Nick pointed out, that's not going to work anywhere where the line is flat because the temperature change is zero at those spots. So anywhere where water changes state, I can't use that formula. So instead, we use the formulas for latent heat. Okay? This latent heat right here, where we go from solid to liquid, or if we're going the other way, liquid to gas, or sorry, liquid to solid, we call the latent heat of fusion. Okay, so in the latent heat of fusion, that's the energy required to separate the solid particles from each other to go to a liquid state. Right? For water, that value is 333 joules per gram. Okay, so if you have 1 gram of ice, which mind you is not very much, okay, it's about 1 milliliter worth of ice, okay, about a cubic centimeter, so maybe about not even quite the tip of my pen. Okay, that much ice would require 333 joules of heat energy to melt if it was already at 0. If it wasn't at 0, you'd have to heat it to 0 first. Ice doesn't melt till it gets to 0. Okay, so is that a fair amount of energy? Does that kind of explain why our hands get so cold when we make a snowball in them? Okay, imagine how much ice you melt when you're making a snowball. Probably 5 or 10 grams. Okay, it's a lot, so your hands are going to get really, really cold. Okay, so the formula to calculate the amount of energy needed to melt a certain amount of ice is E equals m, which is again mass in grams, times LF. That's this number here. All right, so I would take my mass and multiply it by 333 joules per gram. That formula and that number are on your formula sheet. You do not have to memorize them. Okay, so this is the latent heat of fusion. Fusion goes with freezing, F with F. Okay. So that's the amount of energy needed to melt ice, or how much energy is given off when liquid water freezes into ice, because that actually gives off energy. Okay? It's why in the fall, when it's just starting to get cold, okay, but the lakes aren't completely frozen yet, why you'll often see steam coming off the lake. Okay? What you're seeing there is the water releasing the energy as it's beginning to freeze. All right, so would that be a pretty easy formula to use? Take the mass and multiply it by 333. That's it. You are never going to have to manipulate that formula, do anything other than go m times 333. Okay. All right, so that's this part of the graph. Okay. This part of the graph is obviously bigger. It's the biggest part of the graph by far, probably bigger than all the other parts combined. Okay. Turning liquid water into a vapor, or condensing vapor back into liquid. Okay? This is that part of the water cycle we were most concerned with, because it's the one that transports all that energy. Okay? This we call the latent heat of vaporization, okay? Because we're vaporizing or evaporating water. For 1 gram of water, that's 1 milliliter of water, again, same amount, about the tip of my pen, 2,260 joules worth of energy to turn that from a liquid to a gas at 100 degrees. Okay? That doesn't count how much it takes to heat it there, to get it to 100 degrees, at 100 degrees. 2,260 joules of energy. Okay? That explains why steam can burn you so much worse than water. It's got a lot more energy. And why moist air masses moving from the equator to the poles can carry so much energy, right? When you think about how much moisture there is in like a single thunderstorm, okay? We're talking about a lot of energy stored in those clouds. And it's why there's lightning. It's why sometimes we get, the tornado. There's just tons and tons of energy stored inside that cloud, and it's got to go somewhere, okay? Which is why after the storm, it often heats up quickly. During the storm, does it get cold? Okay. Like you can tell when hail is going to happen. The temperature just drops, okay, all of a sudden. Okay. Okay, so lots and lots of energy required to do this step of the graph. Okay. All right, so the formula is E equals m times LV. So just like the last one, whatever the mass is in grams times this number. This is LV. Okay. You won't have to manipulate that. You don't have to remember that formula or the number. It's on your formula sheet. Yep. so if I wanted to do this, how much heat is required to vaporize 2.5 kilograms of water at 100 degrees? So I've got liquid water at 100, I'm gonna end up with steam at 100. That means I'm starting here and going to here. Is there any change in temperature? Okay, so then I wanna calculate how much energy, how many grams do I have? 2,500. So E is gonna equal 2,500 grams times 2,260 joules per gram. Mass times LV. Right? If I do that, it's going to be a big number. $5,650,000 joules. Okay? That is evaporating 2.5 liters of water. Okay? That's a lot. So 2.5 liters, there's 5,650,000 joules of latent heat. That's just in 2 liters, okay? Imagine how many liters there are in a thunderstorm, okay? That's what I'm saying, like when all that water evaporates, those clouds are holding huge, huge amounts of water, okay? That's why that latent heat is such an important energy transfer mechanism, why the jet stream we talked about yesterday is so important because it moves that stuff around. Okay. All right, well, let's look at the type of problem we might run into. I want you to copy this one down, and I'm going to explain to you how it works. Have a question? Yes. Okay, so this is what we call a heating curve question or a heating curve problem, right? So you don't have to remember the formulas, but you have to remember when to use them, okay? And so that means you need to remember this. That shape, the heating curve of water, which is the same shape I had on the last slide, okay? What formula do I use anywhere the line goes up? E equals mc delta T. Okay, and what formula do I use here? This would be 0 degrees Celsius. This would be 100. Okay, what formula do I use here?
E equals MLF.
Right, E equals MLF. Here's where I've got the freezing and melting, so I use the latent heat of fusion. And this one would be E equals MLV. Right, so I know what formula to use at every step. All I have to figure out then is how many steps are there? Which steps are there? And then I just plug in the numbers. Okay? So what you want to do with a question like this is draw your heating curve. You don't necessarily have to put the formulas on it. Okay? What I just do generally is I just draw the heating curve and then I do this. Okay, I'm starting at -15, so that's here. And I'm going to steam at 150, so that's up here. Okay, how many steps am I looking at here? So I've got to heat the ice from -15 to 0. That's 1 step. Then I have to melt the ice. That's 2 steps. Then I have to heat the water to boiling. That's my 3rd step. Then I have to evaporate all the water. That's my 4th step. And then I have to heat the steam from 100 to 150. 5 steps. That's the maximum amount you could get. We don't go any further. We don't talk about going into plasma, okay, because the atomic structure breaks down or anything like that. Okay? So I've got 5 steps. Do I know what those steps are? Okay? I know which formulas to use in each section, so all I've got to do is put in the appropriate numbers. So you would get a mark for that. Okay? For drawing the heating curve so you could establish how many steps and what steps you needed to do. All right, so in step 1, I'm starting at -15 and going to 0. So that's a change in temperature, so I'm going to use E equals mc delta T. All right, They told me my mass, 250 grams. Okay, what's my specific heat capacity? It will be at the third step. Okay, because I'll be dealing with liquid water then. 4.2 is for liquid water. This is the trick. Ice, liquid water, and steam, because water is weird, all have different specific heat capacities. Right? So I actually have to look them up on my chart here, and I see that ice is 2.116 joules per gram. So, and 2.116 joules per gram degree Celsius. All right, how much is my temperature changing by? 15 degrees. I'm going from minus 15 to 0. After that, it's not ice anymore. Okay, and that specific heat capacity wouldn't apply. The most common mistake I see here is people using the full temperature change from minus 15 to 150, and they tell me that it's 165 degrees. Okay, no, I am not changing the temperature of the ice by 165 degrees. Okay, only by 15. Right, so times 15. So that would be my first step. Okay, so 250 times 2.116 times 15 degrees. So that's going to take 7,935 joules. Okay. After that step, I have ice at 0 degrees Celsius. What's it going to do? What does ice typically do at 0? It starts to melt. Do I have a formula that calculates how much energy is required for that? I do. It's this one. E equals MLF. Okay, so in step 2, I'm going to melt the ice. Okay, so we're going to have 250 grams, okay, times 333 joules per gram, the latent heat of fusion of water. Okay, and again, you don't have to memorize that number, it's on your formula sheet. All right, so is that a lot more? It is, okay? It's a lot more energy. Right? It takes a lot more energy to change the state of ice than it does to heat it up. 83,250 joules. Okay, now that that step's done, I've got liquid water at 0 and I'm adding heat to it. What's going to happen? What's going to happen? I have liquid water at 0 degrees Celsius and I'm putting heat to it. It's going to warm up. Yeah. To what temperature? 100. Okay. That's as far as water can go. After that, it'll be steam. Okay. So that's going to be this step. Okay. I just heated the ice, then I melted the ice. Now I'm right here. I'm going to add heat, and I'm going to heat water until it gets to 100 degrees. All right. What formula do I use if I'm changing the temperature of the water?
MC delta T.
E equals MC delta T. Anywhere that line goes up, there's a change in temperature, so I have to use the formula that has change in temperature in it. Okay, and I put in my numbers. Does the mass change? If I start out with 250 grams of ice, I can't have more or less than 250 grams of water or steam at any point. Okay, so still 250 grams, but now it's liquid water, so now I use 4.2. I pointed that out before, okay? And I'm going to multiply by the temperature change. I'm going from 0 to 100. So the temperature change will be 100. Okay, so that is going to take 1,050,000 joules. Okay, is that a lot? That's a lot. Okay, and this is only a cup. This is a cup of water, 250 grams. Okay, that's 1 cup of water. All right, so I've just done this step. Now I'm geared. I've got liquid water at 100 degrees. and I'm continuing to add heat. What's the water gonna do? The water's at 100, and I'm continuing to add heat. What's it gonna do? What does water typically do at 100? It evaporates, yeah. The boiling process that we see is the water turning to a gas and the gaseous water escaping. Okay? The bubbles, that's the escaping of the water. They have the water vapor, right? Because where does the water turn to vapor most likely? At the bottom of the pan where the heat source is. Okay, so you got this water vapor that's got to bubble out of the liquid water to escape. Okay, so we've got step 4. We're going to evaporate the water. Okay, and we have a formula that calculates how much energy is required for that. Okay, E equals MLV. I still have 250 grams of water, and now I multiply by LV, which is 2,260 joules per gram. Oh, I did this wrong, guys. Look what I did. Nobody caught this. I multiplied by 42 and not 4.2. So we got to take a 0 off of here. And this should just be 105,000. That's better. Okay. So on this one here, okay, we're going to have 565,000 joules. Okay, so that number is like more than 5 times this number. Okay, in fact, it's more than all 3 of these steps combined and multiplied by 2. Okay, so the evaporation of water is the most energy intensive step in all of this. Okay, and again, that's why I keep harping on how latent heat can transfer so much energy from one place to another. All right, that's step 4. At the end of step 4, I've got steam at 100 degrees Celsius, and I'm continuing to put heat to it. What will happen to the steam? What will happen to anything if I heat it up? It'll Well, it's already evaporated, so I already have steam. Okay, so I already have evaporated the water. But if anything, if I heat it up, it'll get warmer. Yeah, it's going to get hotter. I can heat steam. Steam can get to be hundreds of degrees Celsius. Okay, so if I keep adding heat to the steam is going to get hotter. Its temperature is going to change. And I'm going to change its kinetic thermal energy. I'm going to make those particles move faster and faster and faster. Okay, which means I'm back to the formula I use anywhere where temperature changes. E equals mc delta T. According to the question, I want to heat it to 150 degrees. Okay, so I take my mass, 250, and I multiply it now by the specific heat capacity of steam. Okay, and you can see that steam is 2.02 joules per gram, so it's got a different heat capacity as well. And how much am I changing the temperature of the steam by? 50. I'm going from 100 to 150. Okay, so it changes temperature by 50 degrees Celsius. All right, so that one's going to require 25,250 joules. Are any of those steps particularly mathematically difficult? Like the toughest part is figuring out the temperature change, really. Okay. Otherwise, all I'm doing is plugging the numbers in and multiplying. What do I have to do with all the numbers I just calculated? Add them all together. Yeah, I need the total. Okay. How much energy in total was required to heat ice from -15 until it turns into steam at 150 degrees? Okay, so I take all those numbers. So in total, to take 1 cup of ice, 250 grams, and turn it into steam at 150 is going to require 786,435 joules. Okay, is that a lot? If you put a cup of ice in a pan at home, yes, it is going to take a very long time before that happens. Okay? And it's going to use a lot of energy, either gas or electricity, whichever one your stove uses. Okay? It's going to use a lot. Okay? That's as hard as they could possibly get, all 5 steps. Okay? Most of the time, I don't ask ones that have all 5 steps because it takes too long. Okay? So the challenge with these is figuring out from the question, which steps do I have to do? Okay, so we've talked about a few of these questions here. Why does putting ice cubes in water make your drink cold? Okay, it's because it takes energy to do what to the ice? What's the ice doing while it's in your drink?
Changing form?
Changing form, right, going from solid to liquid. Okay, and that takes 333 joules for every gram of ice you put in there, right? So it can absorb a lot of heat energy from your drink. Okay. All right, our bodies naturally sweat, so we talked about that. As the sweat evaporates, every gram of sweat that evaporates from your body takes 2,260 joules of energy in order to do that. Okay, the same thing is true if you get out of the shower and you're wet. Okay, you feel cold almost right away because the water on your body is starting to evaporate before you dry off. Okay, and you feel chilled. Okay, because it's taking all of that energy from your body to evaporate. Okay, gardeners often spray their crops before a frost, and this prevents the products from freezing. Okay, so let's say I've got tomatoes, because those are the ones that are most susceptible to this. I know it's going to get down to about -2. If I don't do something, my tomatoes are toast, because they'll freeze. Okay? So I spray them gently with water so that they're covered in a thin layer of water. Why will that protect the tomatoes? It's not so much insulation, but the liquid water is going to turn to ice. And what does it do when that happens? Liquid water has more energy than ice, right? It's changing state from liquid to solid. What does it have to give off? It has to give off heat, yeah, okay? Liquid is a higher energy state than solid. So the liquid that's covering the tomatoes, as it freezes, will release the latent heat of fusion that it held into the tomato and will protect the tomato from freezing. Okay? Now, it only works if it's going to be a light frost. If it's going to get down to -10, you're cooked anyway. Okay? But if it's just going to be a light frost, this will work. Okay? Lots of orchards and vineyards will do that if they're going to have a mild freeze. They'll spray the grapes or the other fruit or whatever, and it can protect them from freezing. Golf courses will also do it with their greens. Okay? They'll turn the water on, and then the water will freeze, but the blades of grass will not. Okay, which is better at keeping food in a cooler cold? 10 kilograms of ice or 10 kilograms of water if they're both at 0 degrees? Which one will keep your food cold longer? Water or ice? It's a common sense answer, guys. I've never seen anyone fill a cooler with cold water. Okay? No one's going, oh, all my food's in there, and fill it up with water. There's a couple of reasons for that. If there's anything in there other than cans of drinks, it's going to get soggy and gross. Okay? And secondly, on the heating curve, okay, we're looking at that heating curve of water like this. Okay? Water at 0 is here. Ice, okay, sorry, water at 0 is here. Ice at 0 is here. Which one can absorb more energy? The ice. The ice can absorb way more energy. That's why we throw ice in coolers. Okay? It absorbs more energy than the water. The water's already changed state. Okay? The ice can absorb 333 joules for every gram that the water can't. Okay? That's why you don't just go over to the hose and fill your cooler with cold water. Okay? You fill it with ice. It does a much better job. All right, and the rest of these are some problem-solving things. So I would like you to try, let's say, question 8. That's a pretty typical exam level question. Okay, I'm gonna give you a few minutes to try 8 and then we'll walk through it. Remember that your first step on number 8 is to draw the heating curve and identify where you start and where you end so you know how many and which steps to do. Okay, give you a couple minutes on that. Okay. All right, so we always said the first step is draw the heating curve of water and then identify where the question starts and where the question ends so that you know how many and what steps you're going to have to do. So, where do we start? It says we have 0.05 kilograms, that's 50 grams by the way, okay, of ice initially at -10. So that's down here because this line here is at 0, so -10 degrees. Okay, and we're going to water at 80. Well, this line's 100, so 80 would be right about there. Right, how many steps am I going to have here? 3 steps. Okay, the 3 steps are, I have to heat the ice from -10 to 0. I have to melt the ice, and then I have to heat the liquid water from 0 to 80. Okay, so 3 steps. What formula am I going to use for changing the temperature of ice? Okay, so I'm going to need a formula for that step. I'm going to need a different formula for the melting of the ice, and then another formula for calculating the amount of heat needed to heat the water. All right, that's as far as I'm going to go for right now. Hopefully that gets people started if they were stuck. Okay, but you got 3 steps. Okay, heat the ice, melt the ice, heat the water. Okay, think about what formulas you use because we wrote those down earlier for each of those steps. Okay, get your numbers plugged in. I'll give you a couple more minutes. So we said there's 3 steps. Okay, in step 1, we're heating the ice from -10 to 0. So that means we're going to have to use E equals mc delta T. In step 2, we're melting the ice. That means we're changing its latent heat. In particular, its latent heat of fusion. So that means E equals m times LF. And then in step 3, I'll start with liquid water at 0, and I'm heating it to 80. That means I'm changing its temperature, so I'm back to E equals mc delta T. The only difference between step 1 and step 2 is I have to use the specific heat capacity for ice in step 1, and I have to use the specific heat capacity for water in step 3. Okay, so for this one here, we'd be looking at 50 grams times 2.116 times 10 degrees Celsius. This one here would be 50 times 333 joules per gram. And this one would be 50 times 4.2 times 80, because we're going from 0 to 80. Okay, so we do those calculations, we add them together, and we should get 34,508 joules. We are going to work on this for the first part of class tomorrow. Okay, and then probably move into starting to talk about biomes. Friday, we will do the Unit 4 exam review. Monday, we will finish up biomes and maybe have some time to do a final exam review, or at least get started on it. Okay, because it looks like we've gained about a half a day. Okay, so that works out nicely for a little extra final exam review time. All right, so that's what we're going to be working on going forward.